Hello, my name is Kanika, and today I'll be presenting our work on meta-attention networks, which is in joint collaboration with Rosemary Nan-Key, Anirudh Goyal, Bernard Sholkoff, and Yoshua Bengio. The classical framework of machine learning is based on the assumption of independent and identically distributed data, which means that the test data has same distribution as training data. Many deep learning architectures that we have are based on layered and monolithic networks, which have different components sharing knowledge across each other. And this sharing of knowledge can lead to potential co-adaptation across different components. In case of any changes in distribution, most of the components need to be changed, leading to potential catastrophic interferences. A learning agent, which is interacting in the world, can be constantly facing changes in distribution, which could be because of the action of the agent itself or because of the actions of other agents. And we need to be able to build such machine learning systems which can adapt to these changes in distribution. A very interesting challenge of machine learning research is this out of distribution generalization and adaptation. We want to build systems which are easy to recompose and have a systematic generalization to enable a fast learning and reuse of the previously learned knowledge. If a distribution changes in a systematic manner, the agent should not have to relearn everything from scratch. Rather, it should be able to systematically reuse whatever it has learned before from its previous experience. In meta-attention networks, we try to address the following two fundamental questions. First is how do we factor the knowledge into components or modules, such that these components are independent, but they can communicate with each other, and at the same time, they are easy to recompose and reuse and adapt. The schematic on the right side shows that if we have factored the knowledge into proper modules, then a change in one of the modules would not mean a change in all of them. These changes can be handled much better in a localized manner. And the second thing that we address here is how do we enable a fast adaptation to new tasks and changes in distribution. The two main ingredients of the meta-attention networks that we propose here are modular architecture and meta-learning. In the modular architecture, we have an ensemble of independent modules such that each of these modules have their own independent dynamics, and these modules are connected to each other through two sets of attention mechanisms, which decide which are the most relevant modules as well as enable a sparse communication between them. In order to learn the parameters of the meta-attention networks, we use a meta-learning framework to learn the different parameters of the network at different timescales. An inner loop is responsible to learn the parameters of the modules themselves, and an outer loop updates the parameters of the attention mechanisms in a slow manner in the outer loop. We ran experiments in the domain of grounded language learning using different environments from the Baby AI and Mini-Grid suite, in which the agent is presented with an egocentric and partially observed view of the environment. It also receives only sparse rewards, and the inputs is in form of RGB images. We found strong evidence that using the meta-attention networks, we can build much more sample-efficient agents. Sample efficiency has been a pain point for many of the deep learning and reinforcement learning algorithms, and we show here that using the ingredients of modularity and meta-attention, we can build more sample-efficient agents. And we saw this behavior across several environments from the Baby AI and Mini-Grid suite. We also found a strong evidence towards building agents which can generalize better in a zero-shot manner using the meta-attention networks. More specifically, we build agents which were trained on simpler environments, but were tested in a zero-shot manner on systematically more difficult environments. And we find that the trained agents using the meta-attention networks generalize much better. We also found very strong evidence towards building better curriculum learning, such that if the source and the target environment share a set of underlying structure, the agent can adapt pretty fast in the target environment, which is also a more difficult environment, using the meta-attention networks. which shows that they can reuse their previous knowledge and they don't have to learn everything from scratch. If you want to discuss more, please visit our poster session from 3 to 4 p.m. Thank you.